our session. And the next speaker is Jiang, who is now in Sobolev Institute of Mathematics. And I know that he is working in very difficult field of association scheme theory, namely in the modular representation theory of association scheme. So, Jiang, please start.
Okay, so firstly, I want to thank Professor Ponomarenko for introducing me. Secondly, I want to thank the organizers of the conference for giving me a chance to report my work. So in this talk, we want to discuss some p-transitive assertion schemes. Firstly, we consider about some preliminaries. Here we consider about the assertion scheme, which we briefly call it a scheme. Here our scheme may not be commutative. So let X be a non-empty finite set. Let S just R0, R1 to Rd be a partition of the Cartesian product X cross X. Then S is a scheme on X if the following conditions hold. We have three conditions. Firstly, the reflective relation. So R0 just pairs X, here X is in X. This relation is in S. And for every R in S, there exists RA prime in S, such that we have the following equality. For any RA, RB, RC in S, and any two pairs, XY, X tilde Y tilde in RC, we have the following equality. And this equality says that the number here is independent of the choices of pairs here. Usually, we will use PABC to denote this number and call it's just an intersection number of scheme. Next, we consider about some basic notation. So S is just R0, R1 to Rd scheme on a non-empty finite set X. For any small x in X and R in S, we set XRA is just a set of all Y's in X, such as the pair XY is in RA. For any X in X and R in S, then set K just a set of XRA. This is called the valency of the relation RA. For any UV subsets of S, then we can define the complex product of UV just set the collection of all RK, such that Ri is in Ru, Rj is in Rv, and the intersection number Pik is less than 0. In complex product, a singleton set is often represented by its single element. So, for example, if U here is just a singleton set with an element RL, then UV here maybe can be written as RLV. Here, we use this notation to denote the closed subset of S generated by the set U. Let SP prime is just a collection of all relations whose valencies are not divisible by P. Here, P is a prime. Here, we consider about sin radical. Sin radical is just the collection of all relations whose valencies is 1. So, sin radical is contained in this set. And we also consider about the sin residual of S. Sin residual of S is just defined like this. So here I have complex product of relations here, and you consider about D plus 1 of them, you consider about this set. And now we consider about, we fix a field F of prime characteristic P. P are here, so they are primes. Let n bar be the image of n under the unitary ring homomorphism from Z to F. Let MXF be the full matrix algebra of F square matrices whose rows and columns are not divisible, are labeled by the elements of X. Regular modules of schemes. Here, all modules are finitely generated left modules. Let IG are elements in MXF. Here, I is just identity matrix in MXF, and G is just O1 matrix in MXF. Let EXY be the 0-1 matrix of MXF whose XY entry is the unique non-zero entry. Therefore, this set is just an F basis of MXF. For every RNS, the agency F matrix is the sum of all EXY. Here, the pair XY is in the relation RA. And this one is denoted by A. For any RBRCNS, then we have the following equations. So A0 is very easy, just an identity matrix. And if you sum all the agency F matrices, you will get all one matrix. And for ABAC, you consider product of them. It gives you just I from 1 to D, P, B, C, I bar AI. Let Fs be the unitary F subalgebra of MXF generated by from 0 to D is AI, all these agency matrices. Then Fs is an Fs module by left multiplication. You can see this equation. This module is denoted by this one and is called the regular Fs module. Trivial modules of schemes. So let V be a one-dimensional F-linear space with a generator V. Formally, define the action AA times V, just K bar V for every RA in S. Then V is an Fs module with respect to the given formal definition, just from the property of schemes. This Fs module is unique up to isomorphism and is called the trivial or principal Fs module. Denote this Fs module by just this notation. For example, we know that all one matrix in this algebra, the F linear space subspace generated by all one matrix is a trivial Fs submodule of this the regular Fs module. This Fs submodule may not be unique trivial Fs submodule in the regular Fs module. But at least we have at least one, but may not be unique. Hanaki and Yoshikiwa, they show that if P doesn't divide the set of X, it implies that this element is in Fs. This element is the block idempotent of a one-dimensional block of Fs. So this condition implies that the regular Fs module has a unique trivial Fs module. In particular, if Fs is a semi-simple algebra, so in this case, using Hanaki's result, we know that in this case, P doesn't divide X. So in this case, we can get the regular Fs module has a unique trivial Fs module. So this is a special case of this one. Motivation. Motivations have two parts. First, you consider about the journal motivation. So the notation or the notion of a scheme generalized the notion of a finite group. The viewpoints and methods from the modular representative theory of finite groups are usually used to study the theory of schemes. Now we consider about the main motivation. Here, let Fg be the group algebra of a finite group G over F. As G acts on itself transitively by left multiplication, the regular Fg module has a unique trivial Fg submodule. We want to study the uniqueness of the trivial Fs submodule in the regular Fs module. The obtained results may be used to study the indecomposable direct summations of the Fs module. For example, we can consider some Scott Fs modules. For Scott Fg modules, this kind of modules are very nice. It's very nice because it has a lot of very interesting properties. For example, they can be parametered by their vertices because they are indecomposable modules. So they can parameterized by the vertices. Now, let us consider about the main results. Firstly, I want to give the following lemma. We want to introduce what is p-transitive schemes. So in lemma 1, let Fp be the prime subfield of F. Then we consider about the regular FPS module. We know regular FS module, but we also know that this regular FPS module just here the algebra is just the adjacency algebra of S over Fp. So we also have this module. This module has a unique trivial FPS submodule if and only if the regular FS module has a unique trivial FS module. The uniqueness, by this one, we know that the uniqueness of the trivial FS module in this regular FS module only depends on P and S and is independent of the choice of the fixed field F, because we have this sentence. So use this sentence to get this conclusion. Now we have the definition. So the scheme S is called a p-transitive scheme if the regular FS module has a unique trivial FS submodule. We are interested in this kind of schemes. Firstly, we have an easy proposition. So if SP prime equals S, in this case, S usually is called P prime valence association scheme. In this case, then S is a p-transitive scheme. Just by computation, we know this proposition. Now, I want to introduce the tools that I use in this work. This is so-called singular subset of schemes. I use this notation because I feel these subsets are very strange. I usually don't understand them. So the definition is just like this. So let T be a subset of S. We call T a singular subset of S if the thing radical is contained in T, and we should have such condition. So this is the complex product RC, RB prime, RB, RA is contained in T for any RA in T, RB in S, and RC in the thing radical of S. For this singular subset of schemes, we'll have the following property. So if T is a singular subset of S, then for this closed subset, the complex product of thing radical and thing residual is contained in T. For this property, we want to consider about the inverse of it. Usually may not be true, but we can have the following lemma. So if T is a closed subset of S, then T is a singular subset of S if and only if this closed subset is contained in T. So by this sentence, we know that this closed subset is itself a singular subset of S. And this is the smallest singular subset of S with respect to the concatenality. And using these lemmas, I can get the following main results. The first main result is that the scheme S is a p-transitive scheme only if S is generated by the union of SP prime and the thing radical of S. This is our first result. And for the inverse, I don't know. So far, I don't know how to prove, but I can consider some special case. For example, in this theorem, so if the valency Ka less than equal to 2 for every R in S, in this case, the so-called coordinate scheme. In this case, then S is a p-transitive scheme if and only if P larger than 2 or P equal to 2 and S equals the complex product of thing radical and thing residual. This is so this property, if you consider about a coordinate scheme, is if and only if. Theorem 9. So if the thing radical, the thin residual is contained in thin radical. Then S is a p-transitive scheme if and only if S is generated by SP prime. So in this case, the inverse of this proposition is also true. So now we can consider about some obligations. So this is the following corollary. We know that if P doesn't divide the size of X, then the scheme is p-transitive. So in this case, using this proposition, we get that S is just generated by the union of SP prime and the thin residual of S. Another corollary, if FS is semi-simple, we know that FS is semi-simple can be used to deduce that P doesn't divide the size of X. So if we have this condition, then we can also have this. So S is generated by the union of SP prime and the thin residual of S. Another corollary. So if P doesn't divide the size of X and P divides the valency K for every relation RA, non-thin relation RA, then S equals the complex product of O of thin radical and thin residual. Another corollary is that if P doesn't divide the size of X and the thin residual is contained in thin radical, then S is generated by SP prime. And next, we consider about some questions. So the first question is that in this work, we define the singular subsets, but singular subsets can be defined for finite hypergroups. Because for finite hypergroups, in the sense of Jiang, we can define thin residual, thin radical, and just like thin. And so singular subsets can also be defined for finite hypergroups. Can they be used to study the structures of finite hypergroups? This, for me, this should be an interesting question. Another question, is the inverse of proposition 7 also true? We know that if a p-transitive assumption scheme, then S is generated by the union of SP prime and the thin residual, but we don't know whether or not the inverse is also true. According to some examples, there are a lot of examples to show that the inverse is true, but so far we don't know how to prove. Finally, a question is about this. So what is the relationship between the scheme and this number? Here, this means that the homomorphisms from the trivial FS module to the regular FS module. Then this is can form a F linear space, and we can suppose dimension here. So we don't know the relation between S and this number. For p-transitive scheme, it means that this number is 1. But this number can be 2 or 3. We don't know. And we don't know the relationship between S and this number. So the results in this question may generalize what we have got here. That's all. Thank you very much.
Okay. Thank you for the talk. And are there any questions, comments? Okay. If no, then I would like to thank speaker again, like you, and we have